Okay, Assalamualaikum warahmatullahi wabarakatuh, and good afternoon, everyone. So today I'm going to explain regarding with the examples on the shear wall frame structure system with torsion. But before we straight on goes to the examples, what we're going to do is that I will explain to you the conceptual theory on the shear wall structure system with torsions. Okay, the first things is that what you can see, let's imagine you have a building structure systems as you can see here. So this building structure system consisting three walls, where you can see this is wall number 1, wall number 2, and wall number 3. And here is you have a rigid frame 1 and rigid frame 2. And you have a distributed loading throughout the structures, whereby the plan view, as you can see in this particular structure system. Okay, so in analyzing this particular structure system, first thing what you have to do, you need to reduce down the structures into idealization systems. So when you do the idealization system and reductions of the structures, what you need to first to do is by excluding the effects of rigid frames, as you can see in figure B. In figure B, what you can see, the idealization is only considering the walls only, whereby the rigid slab is representing as the rigid beam. So here are the rigid beam, and here is the spring wall supports. So the W is acting at the positions where it is allocated at distance A from the origin. And whereby in figure C is idealizing the load acting on the particular structures. So for the wall systems, okay, we can see you have the PI acting, which is PI is the load, point load only acting on the top of the structure systems, whereby RWI is the resistance load that stop the structural wall to move. And this is the PI acting at the top of the frame structure system. So, moving forwards, okay, we can see that figure 3D, E, and F, it's actually show the conceptualizations of the idealizations of the wall frame structure with component stiffness torsion. So in this particular structure systems, what you can see is that, so you have wall 1, wall 2, and wall 3. So then you have a frame. And in this particular structure system, the frame is representing by a spring stiffness. Previously, you are looking that the wall is representing as the spring stiffness, but the frame also need to be representing as the frame stiffness, where you can see in this idealization plan. So in analyzing this structure system, the first structure, what we need to do is that we need to ensure that there is no top movement in the plan view. So in this particular case, you have only a wall structure systems. So in wall structures, you have wall 1, wall 2, wall 3. And the most important thing is that the load being distributed to the wall, okay, must be, sorry, the load distributed to the structure must be in line with the RW. RW is the resultant of the resisting of the load, whereby the resistance of the load should be aligned with W. That is the wind load distributed to the structure systems. And after that, you need to add on with a full structure systems, where you can see that this is representing the rigid frames, and here is the origin. Okay, 0. So in this particular case, you have the KW, and the KF, which means KW is representing the wall frame stiffness. So this is the wall frame, this is wall stiffness, whereby KF is representing for the frame stiffness. And here the structure is only considering the top loading only. So, by looking at this assumption, what we can say is that to solve for the shear wall frame analysis, it is based on the component stiffness method for structure with torsion. The basic assumption that we considered is that the frames are assumed to resist constant shear, whereby there are 2 degree of freedoms are considered at the top structures, which means your rotational movement and also the displacement. And this is the analysis procedure as you can see in figure 3E and figure 3F. So this is considered as system 1 and this is considered as system 2. So when we analyze the structure system, we need to reduce down the structure into system 1 and into system 2. And the next, the RW. If you can see here, we have the load RW. Okay, so let me copy the figure is better so that you can actually clearly see the locations. All right. Okay. So in this particular example, all right, so let's start with this. Okay, so system 1, where you can see this is considered as system 1. Okay, when I said system 1, so here is a system 1. System 1, we are preventing the movement at the top of the structure systems. Therefore, the load being distributed must be resistant by the RW. So this RW, okay, is R is the support reactions whereby it is equivalent to 3 over 8, and then you need to multiply with the lateral loading acting on the structures. Meanwhile, the characteristic of the restraining force, which is the RW, this is the RW, where in other words, we can call it as the characteristic of the restraining force. So when you reduce down the structure systems, this RW must be in line with the wind load distributed to your structures. And the wind load is acting at the center of your center rigidity of your shear wall. Okay, so in this you have this one, and then for the slab idealization is representing as the rigid beam. So in also the floor slab idealization, the floor slab is assumed to behave as a rigid beam supporting by spring support. So the spring support is representing, as you can see here, this is the wall frame stiffness, and this is the K frame stiffness. So in terms of the equilibrium equations, okay, we can see that the unknowns delta and rotation are obtained from the equilibrium equations. So because when we analyze the torsion, we need to determine what is the rotation and displacement. So in this case, the transverse force equilibrium equation, we can see that the total forces that generated by the stiffness, whereby you have KW, KF, and KW, okay, so is opposite direction with the RW. So the total forces is equivalent to the RW. It means that the total forces KI multiply with the delta plus with the X times with the rotation will be equivalent to RW. So this is the equilibrium equations. So then, in order to get the moment equilibrium about the origin, so because you can see that the origin is here, so to get the moment, the each of the forces acting at the shear wall must need to be take a moment at origin. So for the first wall frame stiffness, the xi would be equals to 0 because it is in line with the origin, while for wall stiffness 2, the xi is the distance from the wall to the origin, and this is the frame from the frame to the origin, and similarly to the rest of the particular structure system. So taking moment about the reference point, okay, so then the equation is expanding in this manner, and after that you will get the equation 4. So the structure stiffness has been calculated, ensure, telling earlier. So you have the KW and KF. Actually, the wall stiffness is calculated based on the previous equations in table equation C, where when we did the calculations for the without torsion. Okay, and determination of load on the structure elements. So after solving equation 3 and 4, and you will get the displacement and rotation. From there, the load is carried by the PI is equivalent to KI multiplied with the distance, because stiffness is equals to P delta. So here in equation 5, you get the load resistance by the structure element. And after that, you need to, for the load distribution for two wall system, it is very clear cut because you just can analyze by using simple statics. However, for the load distribution for multi-wall systems, the equation 3 and 4 must be re-established. So finally, you need to combine the results of the system 1 and system 2 in order to obtain what are the total forces acting on the structure systems. So in this particular case, let's look into the examples. So taking into consideration with these examples, we can see that the problem given to you is two wall with 7 frame structures. And the idealizations in terms of plan view is given as you can see in figure A. And bear in mind, in these examples, all calculations are taking into unit meter. So as I said, when you get the first questions, or when you wanted to solve these particular questions, when you have the problems, first you need to reduce down the structure system to system 1. So this is system 1, meaning that from the structure given to you, you reduce down to system 1, whereby you can have this acting as your rigid, the slab is acting as a rigid frame, rigid body, and this is the wall frame is representing by the stiffness, and then the wall 2 also represented by stiffness, and the W is the load, wind load distributed to your structures, whereby 3/8 is the load acting in line with the W. And secondly, you need to draw for your structure systems, whereby we call it as system 2. At system 2, you need to combine everything as original loading, original structure systems, whereby in here you need to represent the wall frame as the stiffness and the spring stiffness as the frame. So in this case, we know that the origin will be calculated from x equals to 0 origin, and then the displacement is measured and the rotational is measured. So in order to calculate this, you need to simply use equation 3. Okay, equation 3, because here you need to know what is the transverse force equilibrium. Transverse force equilibrium is the summations for you in order to find what is your displacement and rotation. So basically, these examples is for you, this equation is for you to get what is the value of the data and also what is the value of the rotation, because this value is needed in order for you to determine, as you can see in the previous slides, for you to determine the PI, which is load carried by each structure element. Okay, but because without this data and rotation, you won't be able to find what is the load acting at the rigid frame and what is the load acting at the wall frame structure system. So for these particular examples, as you can see, so you have equation 3. And then the load given to you in this example, we straightly given to you W is 547 kilonewton. Okay, and RW is, R is 3/8, so you get 205 kilonewton here. So if you have only two walls, and it is very straightforward, 24 is the distance from the wall 1 to the origin, and whereby you have 109, you get 109 kilonewton. And for wall 2 is the summations of 547 minus 109. So then you get the what is the load distribution to the wall 2. But however, if you have a multiple structure systems, meaning that if you have more than two wall structure systems, so if you have more than two wall structure systems, so you need to actually reduce down to system 1 and also to system 2. So in this case, first you need to calculate in this equation, because in these examples, your Ki value is already given. Okay, your Ki value is given as 58 302 kilonewton per meter. So the total wall stiffness for your structure is given as 116640, which is the total up of wall 1 and wall 2. You get 116640. So here, therefore, you get 11664, which is the total summations of your KI and data 1. And what is your KIXI? KIXI is the, because you already know your XI, which means the locations of your wall 1. If you look into your structure, in this example, your wall 1 is located at origin 0. Okay, origin is 0 at wall 1. And your wall 2 is indicated at 120 meter. So from wall 2 to the origin is 120 meter. So here, if you look here, all right, okay, if you look here, you have the value of KIXI, meaning that you have the, you can calculate it by having the first value, which is your 58320 times with 0. So you will get 0. Okay, you will get 0. So, and then summation with the other one, which means you have 58320 times with 120. So here in the end, you will calculate it. You will have, hold on, 58320, okay, times 120. So you will get 699,800. Okay, you will get 699,800. Okay. Oops. So you will get 699,800 rotations. And RW is given in the previous step with 547. So this is equation 1. And this, the second one, the second equations is comes from the uh, moment equation. And this is comes from the transverse force equation. Okay, so you have KIXI data. Okay, KI time XI data. So KIXI, you get 69980. So that's why you get this one. And here is the KIXI squared data. So meaning that if you go to the table, you have KIXI squared. So the first one, KIXI squared, okay, which is this one. You will have KIXI. Hold on, I think there's a little bit mistakes here. So XI squared is 100. I will need to check a bit. 120 squared is okay. And this would be KIXI 58320 times with 120. So sorry, this one is supposed to be 699,400. Okay, so the total here KIXI is 699,400. And here is KIXI squared. So KIXI squared, you can calculate the value of KI and XI squared. So you have 58,320 times with 14,400. So you get around 839 808,000. Okay, so here in total it will be 839,808,000. So those are the wall stiffness. Okay, so in this particular what we call it, structure systems, so you have those particular value. So that's how you get this. So when you have this equation, you can use your calculator to solve and get for what is your delta 1 and delta 1 and rotation 1. So that's why from here, if you calculate the equations, you will get what is your delta 1 and what is your rotation 1. Okay, so and this is coming from the calculator that you are submitting earlier, which means that from this equation, okay, hold on. From this equation, so from this equation, you will determine what is your delta 1 and rotation 1. So from there, once you get the delta 1 and rotation 1, so the next is you need to fill up what is your xi times rotation 1. So you will get 0. And then xi times with 0.472, you will get this value. And you follow the, this one is come from the equation earlier because you are calculating the distance. So delta 1 plus xi delta 1. So this is the value. And therefore you get from the wall load, you get 109 kilonewton and 438, whereby R is 3 over 8, Wi is 109. So you can have 3 over 8 times with 109. So you get 40 over 8. And similarly for this particular same. So this is the analysis of system 1. What is the load resisting force that will be distributed for your particular wall 1 and wall 2. And secondly, you need to calculate for your, what I'm trying to say is you need to calculate for your frame. So for the frame, similarly, so you need to determine. So the first frame will be located at the distance. So you need to look into the systems. Okay, what is the locations of frame 1, frame 2, frame 3, and so forth. Okay, so in these particular examples, so basically we are targeting for this one. Okay, the distance is we are taking from these numbers. Okay, whereby we have 24, 48, 72. Kita masukkan kat sini distance dia. Sebab distance dia I tak tulis kat situ 24. And then 48, 72, 96. Okay, 96, 144, 168, 192. 8 and 192. Okay, so in this case, all right, so here are the distance. So once you get all the distance, so similarly, you need to do just 24 squared. So you get 576, and then 48 squared. So you get 2304, and then you have the 72 squared. So you get 5184, and then you have 96 squared. So basically you get 96 squared, which is around 9216. 144 squared is 2736. And then 168 squared is 28224. And then you have 192 squared is 36864. Okay, so and then again your ki multiplied with xi, so you have the ki. So 199.2 multiplied with 576, so you will get here 114,739 point 2, and similarly you get 199.2 times with 2304. So you will get 458,956.8. And then you have 72 times 5184, which is 373,248. And then you have 96 times 9216, 884, 736. And then you have 144 times 20736, which is 2985984. Here you get 1992, sorry, 199.2 times 28224. So here is 5622220.8. And finally you have 199, sorry, 192, sorry, 199.2 times 36864. So you have around 7343.8. So basically, similarly, you need to calculate your KIXI squared value. So here, when you calculate your KIXI value, so you will get around, hold on. So here is, we need in kilonewton. So the one that you have is in Newton. So this one all need to divide it by kilonewton. So kilonewton kita akan ambil dia jadi sebagai 4.8. So you need to hold on. So 115. Okay, so you have KIXI. So 24. All right, KIXI, you have 20. Oh, itu salah darab pula dah. So this one is the other one. This one is, sorry, this one is for this. Okay. And here is, you need to multiply 199.2 times 24, which is 4780.8. So this one you can change to unit kilonewton. So you divide it by 1000. So this one is 4.8. Sorry. And then similarly here, you have 199.2 times with 2304 divided by 1000. So you have, sorry, 199.2 times with 48 divided by 1000 is 9.56 or 9.6. And then you have 199.2 times with 72 divided by 1000. This one is 14.3. 199.2 times with 96 divided by 1000. This one is 19.1. And here is 199.2 times with 144 divided by 1000. So this one is 28.7. Again, 199.2 times is 168 divided by 1000 is 33.45. And then 199.2 times with 192 divided by 1000 is 38.2. Okay, so all this we need to divide by 1000 as well, because the unit is kilonewton. Otherwise, if you want to maintain in terms of newton, then you can make it this value, but it's too big. 114,739.2 divided by 1000. So this is, so 114, and then this is 1, 2, 3. Okay, and then this one is 372. This one is 8.5. So here is 298. So 1, 2, 3. Oops. 1, 2, 3. So here is 1, 2, 3. Okay, so then you need to sum up this value, which is 4.8 plus 9.6. Sorry, 4.8 plus 9.6 plus 14.3 plus 19.1 plus 28.7 plus 33.5 plus 38.2. So you have here around 148.2. Oops. Two. And here you will sum up 114 plus 459 plus 373 plus 885 plus 2985 plus 5622 plus 7343. So here would be 17781. Okay. So those are the values just come across. Okay. There's something is difference here. Did I calculated it wrongly? 115459. 115,459, 1032. So this one is 1032. Just double check. KIXI 199.2 times 5184. Oh yes, this is supposed to be 1033. 1033. I just double confirm again, sorry. 199.2 times with 9216. So divided by 1000. Okay, this one also wrong. 1836. So this one, hold on, I just double check. 199.2 times with 20736 divided by 1000. 4131. So 199.2 times with 28224 divided by 1000. 5622. Okay, this one is correct. And the last one, just double confirm. 199.2 times with 36864 divided by 1000. 73. Okay, so the total, I will check again. The total 114 plus 459 plus 1033 plus 1836 plus 4131 plus 5622 plus 7343. So you get here around 20,538. Hold on. 538. Okay, so these are the stiffness. So it means that after all, okay, after all, so you will get then this is for the analysis system 1. Okay, and then analysis systems 2, for you to get what is the load. So here is the equation. So you have the delta 2 already solved, and then you have the xi, you need to the distance multiply with the rotations, and you need to add on the displacement and also the rotational effects, and then you will get your spring load and the top load. So this is actually how the structures being distributed. So if you can see, in terms of the calculations, the shear wall with torsion is much more straightforward, because if it is come out in the exams, so all the what we call it, all the equations being given in terms of the stiffness. So it's quite straightforward. Okay, I think that's all. So if you have any questions, please let me know. So in this case, we can say that for the top load, wall 1 will resist 8.9, and this is the one that will be resisted by wall 2. And here are all the other loading that will be resisted by the frame. All right, I think that's all. Thank you very much.